Hey guys, this is my project for experiment. This is Frisbee Dynamics. Let's see. All right, here we go. Introduction. So the purpose of this experiment is to find the angular acceleration of the gyroscope of my phone by using the 2-point formula. So we will apply this formula after testing the acceleration and angular velocity at two locations on a Frisbee and using what we know about the 2 points to derive the position of the gyroscope. The reason I say the gyroscope is because I don't know where that is in my phone, right? But it is centered at whatever position we're taking. So whatever vector that comes in this equation will be inherently by that, and we'll find it in the MATLAB code. So experiment setup, I essentially just tape my phone to the middle and outside of this Frisbee. I try to make it as uh, the outside of my phone is like kind of tangent to the very edge of the Frisbee. It was a little bit jank, but not too bad. That way it'll give me some good measurements. I measured it. My phone's about 6 inches and 3/4 in length and then about 3.5 in width. And so that gave me my center, where I can take my center mass of my phone between the origin, which I put at the center of the Frisbee, and about 3.75 inches to the right, which is where the center of my phone would be in comparison. So the process is just throw this Frisbee 10 feet, and we're going to measure the angular acceleration, or we're going to get the angular acceleration by measuring the angular velocity and the linear acceleration during this throw. And with these 2 points, by throwing it both with the side of the phone and in the middle of the Frisbee. So here's some videos of the throws. Uh, down the hallway. That's first throw measuring linear acceleration. We did these two throws at a time. That does allow for some error. I don't know if I threw these at the same time. You can see right here it dropped. That didn't really affect my data too much. I just had to clip the data down a little bit. So let's look at the data from those throws. So observations. The z-axis due to gravity is the highest, right? And so it's about 10 meters per second, and velocity. So if we look at all the other ones, the velocity was low because the angular acceleration is causing the omega to be higher there. It's the proportion, like omega will be higher at ones where the linear acceleration isn't going to be as fast. So the actual throw takes a fraction of the graph and will seemingly be in median acceleration. I mean, the frisbee is only in the air for about a half a second, and this graph goes about 4 seconds. So I got to analyze these spikes in data. It seems almost immediate, but it gave me my numbers at the extremes of my data. So here's the angular velocity. Um, Now I'm not going to be able to throw this thing perfectly flat. I wish I could, but most of the angular velocity will go in the y direction. My phone is flat against the frisbee. You'd expect it to be z direction, but it was in the y because of my phone being that way. I guess that's how the gyroscope orients itself. So we'll be doing these in the y direction. So with the phone, I throw it. This time I didn't drop it. Although I will say it looks like I threw more up this time. Uh, I don't think that'll affect my data too much. If it does, it should be marginal. Centered linear, the centered linear acceleration data. It's a smaller acceleration than the first throw in. Yeah, that's probably because I threw it up and it seemed to generate a little bit more lift. Besides that, though, we see what we expect in the y direction. It's significantly greater in linear acceleration and significantly less in angular velocity. That's good. That means we didn't screw up too bad. Of course, these are going to vary based on how big my throw power was. It did look like I kind of lofted that second throw a little bit more. Here's some more data. Here's the angular acceleration. As you can see, it's about 20 times less than the last one. Because it's a tenth, and the last one was like a two something. Let's see, ideally this should be zero, but I don't throw perfectly, and the gyroscope actually isn't centered at the middle, so uh, we had to use that. So here's my MATLAB calculations. We put little Sims thing, have it solve for our variables. I inputted the data for my acceleration A, B, omega, and position. And then I did the three variables for alpha here because I was getting some errors with solving for that using the solve function. And as you see here, I tried to take the middle line because that's where if I take my cross product, my z will end up. In doing that, I found my alpha z to be negative 0.6818. This makes sense because as a right-handed thrower, I'm going to rotate it clockwise. Therefore, a negative uh, alpha will make sense because it will lose in the clockwise direction. So conclusions and possible sources of error. Possible sources of error, again, I've said it a couple times now. My throwing power was not the same, and my angle wasn't the same. And then the frisbee is going to wobble different ways in the air. That's what gave us the weird like X, Y, and Z accelerations and mainly angular velocities. And so that might have been a little bit finicky, and that's why some of my variables in MATLAB were like, man, these things don't line up, and that's why I had to take the second line of that code and really solve it, kind of hard code it there. But nonetheless, we got a pretty good number. I think 0.6818 is a pretty solid estimate, given that it was such a short time. It's not going to decelerate that much. So our final conclusions are that the frisbee lost angular velocity at a rate of 0.6818 radians per second squared, uh, and we can find angular acceleration of a rigid body by measuring the acceleration and the angular velocity at 2 points. All right, thank you.